For the band structure, there will be two different bands because this is the EK energy. You have to solve when k is equal to 0, you have to solve so many different solutions. However, for the one below the Fermi level is the valence band. For the one above the Fermi level is the conduction band. And the conduction band have the electron hole as hole. And for the electron, they will for only one subband. For this is the band structure of the indium phosphide. So because here you see the blue shaded area, the Fermi level only have one line. And for the conduction band, but for the valence band, it always have three branch. So it's one branch, two branch, and because these two branches are really close, but there's actually two branch. So this free branch is called the free valence subband because it is the composition of the p orbitals in your atoms. Since you have px, py, pz, and after you mix them together and recombining them in order to the environmental condition, that will give you three different solutions. The three different solutions become heavy hole, light hole, and the speed of hole. So 3 p orbital in, 3 suspend out. So it is reasonable. It's reasonable. And for the conduction band, it's a combination of s orbitals. So one s orbital in, one band out, only one conduction band out. There will be no subband, the conduction band. Yeah, the greater detail. Probably I'm going to describe it again in the lecture 4. But if you really want to know how the this is generated, probably you need to take the time study. But that's okay. This is not the point for this lecture yet. So this is also the proof of block theorem. That's only for your. If you want to know where it is from, you can refer to this part and skip that. Okay. So there is some general trend between the band gap and the materials. For a material with a total lower Z in the unicrystal, the band gap is usually higher. There's a rather simple explanation here. This is the distribution of energy stage, energy levels in the hydrogen. You have 1s, 2s, 2p, and 3s. If your valence band is an interaction between 2p orbital, that means your energy level will be a bandwidth close to its 2p level. And if your conduction band is energy level mixed by 3s orbital, that means your position of the conduction will be also a mix, somewhere around your 3s orbital. Then the energy difference between them becomes your band gap. Alright. So if you are mixing with lighter elements, you are mixing your conduction band and valence band with s and the p orbital with smaller quantum number. So from this figure, you would expect the band gap will be larger. So if I plotted all the 3-5 and the 4-4 the compound semiconductor in this figure, you see when the total Z, the atomic mass, for example, for the diamond, you have 4 carbon in one unicrystal, so the total Z will be 12 times 4, so it's 48. Similarly for all the elements, so you see the one with largest band gap is down the nitron. And when the Z increases, yeah. So for most of the material has the band gap less than 2 eV. So that's when at the beginning people think semiconductor should be the band gap less than 2 eV. But however, when the technology advances, when the gallium arsenide LAT comes, Yeah, because there's some big gap is, so they come to another thing called wide bandgap material. That means the bandgap material is larger than 2 eV. And Professor's expertise is about gallium nitride and aluminum nitride. So now recently, we also find some people invented another method called ultra wide bandgap material. It's something for the material has a bandgap larger than 4 eV. The most popular one is the gallium arsenide, 氧化镓 not the gallium nitride, gallium arsenide, and also aluminum gallium nitride is also possible for that. Okay, this is only for your information. So while you have your bandgap, because the bandgap looks pretty complex, and we want to describe that with a simpler number, but without lost too much information about your band structure. So it is important for a number called effective mass. We already mentioned that in that class. If for a electron in a free space, the EK relation is like that. E is equal to h bar squared k squared divided by 2m. So the relation between E and the K should be a parabolic. However, because it looks like that, and if we were trying to fix the band edge with a parabolic function, we can still do something like that. And then to find what the mass should be to fit the edge of the band. Because while we're doing the statistics, only the profile near the band edge is important. Although the parabolic is not a good approximation, while the energy away from the band edge, yeah, simply it starts to damage. But it is still good enough to describe the size of the EK relation near that. So you can do something like that. You can do the differential, second differential of E by K. Since E is, we call that 2m star h bar square k squared. Then if we take second derivative on k, it becomes m over h bar squared. So we will know that the m squared reverse is equal to h bar squared over 1 squared over dk squared. So you only need to take a second derivative for your band structure near k is equal to 0. Then divided by h bar squared. That will give you the best approach of the mass. And we call it the effective mass. Alright. So the energy band structure near the conduction band now is simplified. It becomes the conduction band in the band edge of K is equal to the position of EC plus an upward parabola. In the other way, the valence band becomes the EE minus a positive parabola. That means the parabola is pointing down, something like that. And this is also actually good enough for the most of the compound semiconductor with the direct bandgap material. So then how do we calculate the total carrier density in the common semiconductor? Let's start with a simpler case, and even not relevant to size physics. Let's consider we have a hotel with many different levels, and the people prefer to live in the lower levels. Okay, so let's For example, if the first floor has 20 beds, and all the beds are occupied by some tourists or customers anyway. Okay, and the second bed has 30 beds. It has more beds, but the population only 70% is occupied. Okay, you have a little bit higher, you have 40 beds here, but only 30% of them are occupied. So the question, how many residents is in this hotel? Yeah, surely you just times how many beds in such a layer times how much is populated by a resident, then sum it up. So for the electron, it's the same case. It's the same way. You have a density of state. That means that at such a level, how many states you have at such a level. Just like how many beds you have in such floor. And the times the probability of this state to be occupied. Then integrating all of that, integrated from EC to the infinite number. Then you get the total carrier concentration. Similarly, the hole will be, because the hole is the non-existence of electron. So the probability is no more F. It's 1 minus F, because we're assuming that F is the probability of an electron. So the P will be integrating from minus infinity to EV, and times the density of state in the conduction band. Okay, that will be total hole in the conduction band. And under equilibrium, 在热平衡的时候 ，N 取 equal to P, or it's not charge neutral, or it's not charge neutral. Okay. So what's the probability of the residence of electron? It comes to the important the distribution called Fermi-Dirac distribution. It only has one variable. It's its Fermi level, the position of Fermi level. It looks like the phone here. I think you must see somewhere, or this class will be too difficult for you. You never see that before. It is 1 divided by exponential E minus EF divided by KT. E minus EF is a form of energy. KT is the energy, so this is a unitless value. Then you take exponential plus 1, then take inverse. This is the case of Fermi level. So if you take a quick observation, you will know that when the energy is in Fermi level, E is equal to F, its probability of existence will be half. 就存在几率是1半。So what does that mean? That means the electron will try to hop in and try to hop out with the same probability. So it will be something like an average energy of that system. Because we said that if your energy is high, the electron try to leave because it might go to the lower energy, right? But if the energy is low, you have some probability to be excited from the environment because the environment isn't in absolutely zero. So there will be some equilibrium energy that the probability of electron goes in and hop out will be equal. So that's a characteristic of a system. 它就是一个系统的一个特征。Alright. So the relation can be described by this. Alright. So in order to calculate the density of state with effective mass, is a really simple procedure. You just assume what happens with free electrons and change the mass from M0 to your effective mass. It could be NC or MB. Then the same rule will apply. For example, for a particle in the box, if you need to refer to your quantum mechanics or modern physics textbook, that will surely definitely that would be right. Well, I don't know what they are trying to do in the modern physics. In a condition particle in the box field, the density of state, because the energy is written in such way, E is equal to blah 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 blah. That is all constant divided by a positive number squared. So since one number is a state, so you are trying to type from E to DE how many points will be included in such being shell. And the result is that though E should be 2 pi over 1, 2n over x bar squared times 3 divided by 2 square root E. Alright. So this is the result we derived from the particle in the box for the simple quantum mechanics. But for the solid, we can just directly borrow this result, just changing few terms. First, the M0 goes to M star, because you are mimicking the electron with a free electron, but different mass. So you just change M to M star. Second, because now the energy doesn't start from 0. It started from a low level value called EC. So the energy you should not just write it E. Since you are drawing a band structure, this is the energy, this is the K. Since you are drawing two bands in the same figure, you must define a 0 about where it is. For convenience, we usually assume here EV is 0. So the point here, you didn't refer to the energy here. You are trying to refer to the EC here. And the reason why we refer EV is 0, actually it doesn't need any reason, it's just a convention. Yeah, that will be easier for many people to unify the notation. We usually assume the top of the valence band to be 0. Then we can no more just write it down square root E. Yeah, or that will be unphysical. This parabolic is starting from EC, not from E equal to 0. Alright. So the second, you need to remember that the term here you need to E minus EC. Then this is the more reasonable way to write down the density of state. Alright, if you do the similar thing to the very thin material, for example, a quantum wave or thin plane, or we can say particle in a two-dimensional box. Let's consider semiconductor is much narrower than the two other sides. Because the dimension in X is very different from the other two. So you need to pull this out and do the synthetic layer by layer. So you have a much more dense grid at n is equal to nx equal to 1 plane. And n is equal to this another plane. So if your total energy is less than E2, for example, you are counting the state in such a small sphere, the density of state tells you it should be a constant. Following the same procedure in doing the density of state. However, if the energy is a little bit higher, let's see. Let's assume the total energy is on such a sphere. It will include the two planes. So you need to do the statistic at the first plane. Then also do the second static at the second plane. Then sum it up. So when your energy is higher than E2, the density of state will double. Because you need to calculate density of the state from two planes. Similarly, if you become higher and higher, the density of space will increase. Then here we have a general relation. If the energy is between the nth level and the n plus 1 level in the x direction, then your density of state will be a constant times n minus 1. Alright. For example, if it is okay, I think I made some mistake. It is since when it's larger than 1, it shouldn't be 0. When it's larger than 1, it is 1. Yeah, so I will make a correction here. It will be it's n times this number. Alright. So now we can draw both density of state of the quantum wave and the bulk. You will find that these two should be consistent. Since we are in the same physics world, we shouldn't be inconsistent. But this is the density of state in bulk derived. It is a square root relation, something like that. Okay. And this is the density of state of a quantum wave. When it is higher than the ground state, how do we calculate the ground state? That's what we did in the last 1 hour. So this number can be calculated also by numerical. Yeah, and I only teach you how to solve the ground state. Since where exactly the EX2 and EX3 is actually not so important for laser diode. I'll tell you why when the time comes. Anyway, so let's see if the energy is less than EX1, because there's no state here, the density of state should be 0. But when the energy passes the EX1, past its ground state, then it suddenly hops up to a ground state to be n divided by pi Vx h bar squared. It is a constant until it passes the second energy state in that quantum wave. Okay, it added up once, and so on and so on. You see, this level, if the d is very large, this level will be small. The first level will be small, but the EX1 is also small. So if the EX1 become very large, it will be something like that. It will be start here, then eventually merge to the density of state in the 3D case. Yeah, so that means this should be consistent. We want that to in reasonable phase. These two bulk case and the quantum waves, they are actually the same thing.